Hello, I'm William Hudnut,
I'm Cameron Melman.
and we are presenting on our method for pre-processing orbital ephemeris data for use by an optimizer to support multi-capture satellite debris removal operations.
By the end of 1957, there was a total of 3 man-made objects in orbit around Earth. A little over 6 decades later, today, there's an estimated over 100 million pieces of debris orbiting Earth at every moment. The majority of this debris is fairly small, being only millimeters in diameter. However, it still poses a massive threat to spacecraft and satellite because of the speeds they travel at. Debris travels at hypersonic speeds of over 7 kilometers per second. Therefore, a collision with a piece of debris only millimeters wide can cause significant damage, while a collision with a piece of debris centimeters wide can be catastrophic for a spacecraft or satellite. On the right, you can see an image obtained from NASA that shows the growth of debris and craft in orbit around Earth from the 50s to today. On the bottom left is an illustration of this debris orbiting Earth. It should be noted that both of these images only include debris of 10 centimeters or larger, so the majority of debris actually orbiting Earth is excluded from both these images. To this day, aside from the ESA and NORAD tracking hundreds of thousands of pieces of debris, spacecraft, and satellites, there has been little to no proposed solutions to solve or even ameliorate this massive threat to the space industry. OSCAR, which stands for Obsolete Satellite Capture and Removal, is a 3-unit CubeSat satellite designed to capture and deorbit space debris. OSCAR's mission works in 4 steps. It is first fed 3 to 4 targets. OSCAR is capable of deorbiting 3 to 4 targets ranging in size from 1 to 20 centimeters. OSCAR then individually pursues each target, capturing them with a weighted net. Then, through the use of electromagnetic tethers, the debris and net are dragged back into Earth's atmosphere where they burn up upon reentry. And finally, OSCAR drags the final piece of debris along with itself back into Earth's atmosphere through the use of its excess fuel, where they both will burn up. As previously stated, because NORAD and the ESA tracks thousands upon thousands of pieces of debris, and most of this ephemeris data is accessible, this can be used to find the final 3 to 4 targets. However, because these lists can be 10,000 lines long, it needs to be significantly shortened before a computational heavy optimizer is used to get the final targets. In addition to this, OSCAR is a CubeSat satellite and therefore has considerable fuel restrictions. So the algorithm that is used to shorten the larger list to a much smaller one before the final targets are found must greatly consider which pieces of debris are within OSCAR's fuel range.
In order to provide usefully sorted target data to the user, these procedures must be completed. First, the TLE data must be processed to extract the classical orbit parameters used by the filter sorter algorithm. Second, the algorithm must be run on the data to extract the orbital transfer delta V costs for each potential target. Thirdly, the potential targets and their associated data must be sorted to select only the ones that OSCAR can in fact access, and then output in a file format useful for later processing by an optimizer routine. The TLE data files used to develop the system contain all necessary data for later processing, so the wrapper was used to perform both the first and third steps enumerated, reducing the length and complexity of the transfer delta V calculation algorithm. The transfer orbit method chosen was a non-Hohmann 2-impulse transfer orbit. This orbit's transfer cost can be calculated in a single step rather than via an iterative process. The method is to perform a departure burn at either the ascending or descending node of the initial orbit, and then a capture burn at the opposed node of the target orbit. All plane change is performed at the larger orbital radius to reduce the fuel cost of the plane change, and the impulse at the smaller target orbital radius is constrained to be purely tangential. A full derivation of this method is contained within our paper. The method requires the semi-major axis, eccentricity, right of ascension of the ascending node, inclination, and argument of periapsis of the initial and final orbits. The algorithm is implemented in the function nh delta v, which calculates both the ascending and descending node departure and arrival burns. Based on the initial and final radii of each transfer orbit, it determines which burn will contain the necessary plane change. Once the transfer delta v for both orbits has been calculated, the function selects the lower delta v path and appends the delta v cost and the information about the transfer path, including node where the transfer is initiated and whether the transfer is from a higher orbital radius to a lower orbital radius or a lower orbital radius to a higher orbital radius, to the data file input to the function. Two supporting functions are required for this function to operate. One is a function which calculates the true anomaly of the line of nodes of two inclined orbits on each orbit, and one is a function which calculates the 1-3-1 Euler rotation matrix from a parafocal orbit frame to a Newtonian orbit frame.
In order to validate and both understand the results of this algorithm, there needs to be some understanding of where the most amount of debris in orbit around Earth is expected. On the right, you can see a chart obtained from the ESA on the spatial density of debris in orbit around Earth based off of altitude and declination. It can be seen that the maximum amount of debris is expected to be at an altitude of about 800 to 900 kilometers with an angle of declination of around 98. Using this data, and as well as the assumption that most of the debris orbits are going to be near circular, we ran the following simulations. These simulations were done using a list of a little over 10,000 pieces of debris ephemeris data and a fuel restriction of 450 meters per second. An initial orbit was chosen for Oscar, and then the amount of attainable debris from this initial orbit was returned. On the left, we used an initial orbit that was at an altitude of about 900 kilometers, near zero eccentricity, inclination of 98.6 degrees, and we varied the right ascension of ascending node from 0 to 180 degrees. The angle of periapsis is pretty much irrelevant because the orbit is near circular. As you can see, there was an average of about 20 pieces of attainable debris at every orbit until the right ascension of ascending node increased near 180, where it spiked at the end. However, when we ran a very similar simulation with an inclination of only 0 degrees, we got completely different results of 1 to 2 pieces of attainable debris per orbit, with a worst case of 0 and a best case of 4. Referring back to the chart in the previous slide, all of this does correspond with that data. Going forward, we completed 2 other simulations using eccentricity and altitude as the variables that we changed, and you can see that they also correspond with what is expected. The most amount of attainable debris can be found at around 800 to 900 kilometers, while at an eccentricity of about 0.01, there is also the maximum amount of debris Oscar can capture from its initial orbit. This data is not only promising because it corresponds with what we expected to see, but it's promising because it means that if Oscar is put in the correct initial orbit, there is a considerable amount of possible targets for Oscar to deorbit.
There are some known issues with the algorithm, however, including the fact that it does not in fact calculate an optimal orbital transfer. Oscar is capable of more than a 2-impulse orbital transfer, and therefore a somewhat more optimal transfer path can be calculated between orbits. So some debris that Oscar could capture would be left out by this algorithm's sorting process. However, this is acceptable because it also reduces the computation time of the optimizer. Some of the debris, however, that is tracked is in highly eccentric orbits, which also run into an issue with this particular method of orbital rendezvous. Node-to-node transfers are not preferred for transfers to a highly eccentric orbit, especially if there is a low difference in inclination between the two orbits. In these cases, apps-to-apps transfers are much more efficient, but are not implemented in the delta V calculation routine. However, most debris in the size range under consideration for capture by Oscar is, in fact, in a low eccentricity orbit, and the physical limitations of the CubeSat's propulsion system prohibit transfers to most highly elliptical orbits in any case, since those orbits generally require a significant delta V budget to enter. This algorithm has performed quite well in testing. It is capable of filtering a 10,600 element TLE database retrieved from spacetrack.org, which was used as the test file, to an 82 element target set in just over 2 seconds on a standard personal laptop. Given the complexity of finding a truly optimal 4-target path for Oscar from a set of targets, reducing the size of the target set should greatly reduce the computational cost of producing such a 4-target path for the CubeSat. In addition, the method is flexible and can produce such a reduced target set from any data format so long as the wrapper file is edited to correctly extract the classical orbit parameters required from the data. Thank you very much for attending our presentation, and if you have any questions for us, please let us know. Thank you and stay safe.